Hi students, welcome to the video lecture 1 on the topic laminar and turbulent flow, which is taken from module 3. The today's class will derive the derivation on the flow through circular pipe, which is also called as the Huygens-Poiseuille equation. So this Huygens-Poiseuille theory, it is based on the following assumption. That means the fluid which is flowing through this circular pipe, the fluid follows the Newton's law of viscosity. That is shear stress, that is given by tau is equals to mu into du divided by dy. And there is no slippage of the fluid particles at the boundary. That means the fluid particles adjacent to the pipe wall will have zero velocity. This is the nature of the fluid. That means the first layer of the fluid particle, when it comes in contact with the solid surface, it sticks to the surface. That means no slippage of the fluid particles will take place. That means the fluid velocity will always be zero at the solid surface. So consider the same sketch we have taken here. Consider a horizontal circular pipe of radius r. This is the radius r, having a laminar fluid flowing through it. So in this circular pipe, horizontal pipe of radius r, having a laminar fluid flowing through it. Laminar fluid is flowing through it. So consider a cylindrical fluid element of radius small r. The radius of this cylindrical fluid element is small r and length dx. This cylindrical fluid element, it is sliding in a cylindrical fluid element of radius r plus dr. So this is this circle, this is the radius of this cylindrical fluid element. So another fluid element is there of radius r plus dr. So this is the thickness dr, so its radius will be r plus dr. So this cylindrical fluid element of radius r and which is having length dx, it is sliding in a cylindrical fluid element of radius r plus dr. So now what are the forces acting on this fluid element? We'll study. This pressure P is acting on this face AD, that is on the left end, or we can call that pressure P is acting on this cross-sectional area AD, which is in the direction of the flow. That means cross-sectional area of this fluid element on the left hand, it is given by pi r square area. P into pi r square is acting on the left end, whereas pressure force P plus dou P upon dou X into dx, already I have written here, pressure force P plus dou P upon dou X into dx is acting on this face BC, that is on the right end of this cylindrical fluid element. So this indicates P indicates pressure plus dou P upon dou X indicates change of partial pressure in the X direction through a distance dx is acting on this cross-sectional area, that is pi r square, which is acting opposite to the direction of the flow here. You can see here. Then another force, that is shear force, which is given by tau, it is acting on the surface of this cylindrical element. So surface of this area of this cylinder is given by 2 pi r into L. Here L is nothing but here dx. Dx is the length of the cylindrical fluid element. So the shear force is acting on the entire surface of this cylindrical fluid element. The surface area of that cylindrical fluid element is given by 2 pi r into dx. So now for steady flow, the net force on the cylinder must be zero. That means the net force acting on the cylindrical fluid element must be zero. Now we have written those equations. It is P into pi r square minus dou P plus dou P upon dou X into dx into pi r square minus tau into 2 pi r into dx equal to 0. So if I will elaborate this equations, P into pi r square minus P into pi r square, this will be minus dou P upon dou x into dx pi r square minus tau into 2 pi r into dx equal to 0. So this P into pi r square, this P into pi r square gets cancelled. So my equation remains in this form. So I have shifted this equation to the right side. So my final expression will be minus dou P upon dou x into dx pi r square equals to tau into 2 pi r into dx. So the terms which are common I have cancelled on both the sides. So therefore this tau will be equals to minus dou P upon dou x into r divided by 2. So let me call this equation as equation 1. So this equation shows that flow will occur only if the pressure gradient exists in the direction of the flow. So already we know that if the fluid wants to flow through the pipe, there should be a pressure gradient. If there is no any pressure difference, then the fluid will not flow through the pipe. So this is the shear stress distribution across the circular pipe. It is shown in the sketch here. So now we will calculate the velocity distribution. So from Newton's law of viscosity, we know the equation, that is the shear stress tau is equals to mu into du divided by dy. So in this equation, this distance y is measured from the boundary, that is small y is given by capital R minus r. So I will tell you, y is measured from this boundary of the circular pipe, that is from the wall of the circular pipe. So this y is equals to, this radius is capital R and the radius of this cylindrical fluid element is a small r. So therefore this capital R minus small r gives me this distance, y distance. So the same I have written here, small y is equals to capital R minus small r. So if we differentiate this equation, dy is equals to minus dr, because this r is constant. This r is going to vary, that is minus dr. So this dy value I will substitute in this equation. Therefore this tau is equals to mu into du divided by minus dr. Same equation I have written here, tau is equals to minus mu into du divided by r. Let me call this equation as equation 2. So if we will compare the equations 1 and 2, in the equation 1 already we have proved that tau is equals to minus dou P upon dou x into r divided by 2. It will be equals to minus mu into du divided by dr. So with this equation, let me write the equation in the form of du divided by dr, because I want to calculate the velocity distribution. First I will separate this term. So I will write du divided by dr is equals to 1 upon mu dou P upon dou x into r divided by 2. By comparing equations 1 and 2, I have written this equation. So here r divided by 2. Let me write the same equation here. I will separate this u term one side and I will shift this r term to the right side. So therefore du is equals to 1 upon 2 mu dou P upon dou x into r into dr. So if I will integrate this equation with respect to r, then integration of du will be u, that will be equals to 1 upon 2 mu dou P upon dou x as it is. So integration of r into dr, this will be equals to r square divided by 2 plus c. The same equation here, r square by 2 is there. I will multiply here, I will take this to this side. Therefore u is equals to 1 upon 4 mu dou P upon dou x into r square plus c. So this is my equation for the velocity distribution equation. We call this equation as equation 3. So where this c is constant of integration and it is obtained from the boundary condition. This value c, it is obtained from the boundary condition. So let me apply the boundary condition, that is at small r is equals to capital R. If you will substitute this small r equal to capital R, their velocity u will be equals to 0. That means this small r, if I will take equals to capital R, at capital R here, at the pipe wall, the velocity u will be equals to 0, because there is no slippage of the fluid particles. That means velocity u will be equals to 0, and I will put the condition small r is equals to capital R. This u value I will substitute in equation 3 here. That is u is equals to 1 divided by 4 mu dou p upon dou x. This r I will replace it by capital R, that is r square plus c. So with this I will calculate the value of c. Therefore c is equals to minus 1 upon 4 mu dou p upon dou x into capital R square. Now let us put this value of c in equation 3 here. So now u is equals to 1 upon 4 mu dou p upon dou x into r square, where this value of c is given by minus 1 upon 4 mu dou p upon dou x into capital R square here. So therefore u is equals to minus 1 upon 4 mu dou p upon dou x I have taken common. So this equation will be equals to capital R square minus small r square. So this equation, let me call this equation as equation 4. So this is the final expression to calculate the velocity distribution equation for the flow through a circular pipe. So this is the velocity distribution sketch through a circular pipe. It is shown here in the sketch. So next we will calculate a ratio of maximum velocity to the average velocity. So now let us calculate first maximum velocity. So when will be the velocity will be maximum? The velocity will be maximum when this r is equals to 0 in equation 4. That means when r is equals to 0, that means at the center of the pipe the velocity will be maximum, because at the pipe wall, at both the sides of the pipe wall, the velocity u will be 0. So its velocity goes on increasing like this way. At the center of the pipe the velocity of the fluid will be maximum. For that purpose we have written here the velocity is maximum when r is equals to 0 in equation 4. When r is equals to 0, then we are going to get the maximum velocity. Therefore u maximum is equals to minus 1 upon 4 mu dou p upon dou x into capital R square. We have put small r equal to 0 in equation 4. So this is the equation for maximum velocity, where maximum velocity is calculated by this formula minus 1 upon 4 mu dou p upon dou x into capital R square. Let me call this equation as equation 5. So now equation 4 is rewritten as u is equals to minus 1 upon 4 mu dou p upon dou x. R square I will take it as common. If I take r square common, then this will be equals to 1 minus small r square divided by capital R square. So if I will elaborate this equation, then I am going to get the equation 4 only. But the equation 4 is written in this form. U is equals to minus 1 upon 4 mu dou p upon dou x into capital R square. R square only I have taken common. So in the bracket 1 minus small r square divided by capital R square. So this minus 1 upon 4 mu dou p upon dou x into r square is nothing but u maximum. So this value I will substitute, replace it by u maximum. Therefore u is equals to u maximum in the bracket I will write as it is 1 minus small r square divided by capital R square. Let me call this equation as equation 6. Now the discharge through an elementary ring of thickness dr is given by. So now what is the discharge through this elementary ring of thickness dr? Now we are going to calculate the discharge through this area, that is dr, thickness dr. How much discharge is going through this much area now? Whereas dq is we are going to calculate only for a thickness dr, elementary ring. It is elementary ring. This is in the ring shape, elementary ring which is having thickness dr. dq is equals to u into the discharge is given by area into velocity, where u is the velocity, area, that is surface area of that elementary ring is given by 2 pi r into dr. The elementary surface, the area of this elementary ring, it is given by 2 pi r into dr. So dq is equals to dq, where u is nothing but this value, the same value I will substitute here, where u is given by u maximum in the bracket 1 minus small r square divided by capital R square into 2 pi r into dr. The same equation I have written here. So now this is the equation for elementary ring. Now if I want to calculate the total discharge, that is q, that will be calculated by integration of this dq over the limits 0 to capital R. Total discharge is calculated by integrating this equation over the limits 0 to r. So now let us see here, total discharge Q is given by this equation. So Q is equals to, with the limits 0 to r, this dq is given by u maximum in the bracket 1 minus small r square divided by capital R square 2 pi r into dr. Dq equation only I have written here. So where 2 pi into u maximum I will take separate outside because these are constant. 2 pi into u maximum velocity is constant, it's fixed. So over the limits 0 to r I will integrate this term now. 1 into r is r, so r square into r is r cube divided by r square in the bracket complete dr. So 1 into r square into r, the same equations I have written here. Now 2 pi into u maximum, so if I will integrate this, r into dr will be r square divided by 2 minus r cube into dr will be r to the power 4 divided by 4 r square as it is with the limits 0 to capital R. So where r is there, we'll substitute this capital R, and anyhow this term is going to be 0 only. So 2 pi q maximum is same as it is equation I have written. So this I will put these values where r square divided by 2 minus r to the power 4 divided by 4 r square. So here r square term and r square term gets cancels here, so my equation will be remaining 2 pi into u maximum r square divided by 2 minus r square divided by 4. So here LCM will be 4 only, so this will be 2r square minus r square, this will be r square only. So my final expression will be q is equals to 2 pi into u maximum. So if I will solve this, so my final expression will be r square divided by 4. So again here 2 and this gets cancels, so my final expression q will be equals to pi divided by 2 r square into u maximum, where total discharge is given by this formula. Q is equals to pi upon 2 r square into u maximum. Now with this let us calculate the average velocity of the flow. So whereas average velocity of the flow is calculated by the symbol u bar, that is u bar is equals to total discharge divided by area. So total discharge is given by pi upon 2 into r square into u maximum, whereas area A is given by, that is area of this circular pipe, whole circular pipe, because we have calculated the discharge for this circular pipe, entire circular pipe, that is pi r square. So pi gets cancels, r square gets cancels, so therefore average velocity u bar will be equals to u maximum divided by 2. Let me call this equation as equation 7. So we can write the same equation, that u maximum divided by u bar is equals to 2 also with this equation only. So equation shows that average velocity is half of the maximum velocity, or this equation 7 can also be written in this form: u maximum divided by u bar is equals to 2. That means maximum ratio of maximum velocity to the average velocity is equals to 2. So in the exam he may ask, prove that average velocity is half of the maximum velocity, or prove that average ratio of maximum velocity to the average velocity is equals to 2. So up to here you have to derive the equation. So next, drop of pressure for a given length L of the pipe. So equation 7, it shows that average velocity u is half of the maximum velocity. So where u bar is equals to, let me substitute the value of this u maximum here, minus 1 upon 4 mu dou p upon dou x into capital R square. U maximum value is given by divided by 2 as it is. Then this equation will be equals to minus 1 upon 8 mu dou p upon dou x into capital R square. So with this equation only I have written the equation in this form, that is 8 mu into mu bar into dx cross multiplication, 8 mu bar into dou x, that will be equals to minus dou p into r square. Equation remains as it is, the same equation I have written in this form. So as I want to calculate the drop of pressure I want, so I will separate this dopey term one side and I will take all the other terms to the right side. So therefore minus dopey, that will be equals to 8 mu bar into dou x divided by capital R square. So if we integrate this above equation with respect to x, so integration of minus dopey over the limits 1 is to 2, that means over the section 1 to section 2. So that will be 8 mu bar divided by R square will be common. So integration of dou x over the limits x1 to x2, over the limits x1 to x2. You can see here in the sketch I have drawn here already. This is for the length of the sections of the pipe. This is x1 over the limits up to x2. So integration of dou p will be p, that is minus p. The limits 1 is to 2, 8 mu bar divided by R square. Integration of dou x will be x over the limits x1 to x2. So if I will simplify this equation, this will be x2 minus x1. So minus sign I will take outside common. So this will be p2 minus p1. So minus sign I have kept as it is. This is p2 minus p1. Same equation I have written here. 8 mu bar divided by R square in the bracket x2 minus x1. So minus into minus plus. So I have written the equation in this form. P1 minus P2 equals to 8 mu bar divided by R square. Whereas x2 minus x1 is replaced by L. You can see here. This distance is x2 minus x1. That will be equals to L. So I have replaced x2 minus x1 by L. So P1 minus P2 is equals to 8 mu bar into L divided by R square, where R is nothing but half of the diameter. So P1 minus P2 is equals to 8 mu bar into L, where R is replaced by D divided by 2, half of the diameter, whole bracket square. So this will be 8 mu bar into L divided by D square divided by 4. So P1 minus P2 will be equals to 32 mu bar L divided by D square. So P1 minus P2 is nothing but the drop of pressure here. So loss of pressure head, how will calculate pressure head? That will be calculated by P1 minus P2 divided by rho g. In the Bernoulli's equation already we have proved it. P divided by rho g, it indicates the pressure head. So here loss of pressure head is given by P1 minus P2 divided by rho g. That will be equals to 32 mu bar L divided by rho into g into d square. That means this equation I have divided the equation, whole equation, by rho into g term. So this equation is called as the Huygens-Poiseuilles formula. So this is the very important derivation which will be asked in your final exam. Surely if it is asked, it will be asked for 10 marks question.